Yeah, a short word about PROTOS. Who is PROTOS? We focus on the development of software tools, test tools, and software architecture for embedded systems. Today, the focus will be test tooling, and that's me. I'm Thomas Schütz. I'm an aerospace engineer. I love embedded software architecture, tests, and tools. That's what we do. And I'm the CEO and founder of PROTOS. So, what are we doing today? What we're looking at, why are we doing what we're doing? Let's start with the biggest pain, or with a big pain many developers in the field of embedded systems have. The tests get more and more expensive and get slower and slower if you progress in your project. So a unit test is still relatively inexpensive, fast, near at the development. And the integration system test, so after release, it gets really expensive and really slow to test. And what we do with the miniHIL is we bring the system test and the integration test to the desktop of the developer or to the continuous integration for complete automation. So we need to test and we need to learn earlier to speed up the development process and bring down the costs as well and bring up the quality. In order to explain what the focus really here is, we have a look at the development process for embedded systems. Very typical approach is to start on an evaluation board, to develop drivers, and then the next step to develop hardware-related software components, such as motor controls or battery controls, bus protocols. So anything that has really a close relation with hardware. And then on top, usually is developed an application or software components, and you integrate this to an application. And in the end, the application is run probably first at the evaluation board and then on the real ECU. So let's have a look at where is usually tested. So with the unit test, you can test software components very good. So pure software components, here the unit test is a real effective way to test them. Fast, cheap, good to automate, so please continue doing that. And in the end, usually you have a system test, a real system test or a simulated system test with a hardware in the loop test system. The problem with those approaches is they are usually very late in the process. So they are done in another department, and they're usually too late for the software developer or for the developer of the embedded systems. And what we do is we focus with the miniHIL on the integration test or a HIL system test early in the process, so completely during the whole development process with automated testing. Most embedded projects are not tested in those early phases, or at least not sufficiently tested and not automated tested in these phases. So what do I really want and need when I develop embedded systems with respect to tests? You want to test every code change of every developer within minutes instead of weeks. You want a full regression test also for unrelated code to detect side effects of your changes. You want full test automation to enforce the tests. So every commit should be tested. And in the end, you also need automated hardware in the loop tests to test more than just pure software units. Unit test, as I said, is really good, but it's not sufficient to really test your embedded system. So why is it so hard to automate tests for embedded systems? Let's have a look at a typical example from a project, a real world project. The temperature shutdown for all border values of 300 relevant system states. It's been a safety critical project with a motor control system. And what the customer had before was a climate test chamber. The complete ECU was tested, including the motor, including the temperature sensors, and so on. And the problem was that every test for every state took a couple of hours. And in the end, it would have been necessary to test for something around 30 days to really test all the border values for all the system states. And that's never done. So and it was not really automatable. So what we did is we took out the microcontroller and just tested the microcontroller with the drivers, with the application software. So complete software as it is, but we simulate all the IOs at the pins on signal level. And this speeds up the testing process by orders of magnitude, because we can just simulate the temperature sensor and the motor and things like that, which reduces the test per state to 10 seconds. So in the end, we needed to run this for 50 minutes to really test the combinations of all relevant states and shutdowns and so on. So that's a really huge benefit in terms of development cycle and costs. So what are the typical response times for the different test levels? So let's have a look at the right leg of the V model. If you talk about component tests, I'm talking about unit tests here. Usually you need to wait a couple of minutes. You can run this on your desktop, the tests. So that's a really, really fast way to have your first test. Integration test usually is not done, at least not very often. The system tests, hardware in the loop system test or real system test, usually is run, and those are really the experiences of our customers and of our projects. The system test is usually run in between 2 and 12 weeks. So it doesn't take 2 or 12 weeks to run the test, but it's not done very often because it's extremely expensive. And usually the equipment is not free for this test because the equipment is so expensive. And the acceptance test, which is basically on the same level as the system test, also takes between 2 and 12 weeks. So what we do is we bring the integration test into the game here with the miniHIL. On the right side, you see the miniHIL board. Here you have an Oryx adapter to test an Oryx automotive chip, but we also can test any kind of 16 or 32-bit controllers, 64-bit also if you want. This integration test is completely automated since we only test the pins of the microcontroller. We can simulate all the interfaces, and by that reducing the turnaround cycle for the tests to minutes instead of weeks. That's really a big benefit here. So we have a very fast turnaround by test automation, and by that we close the testing gap we have seen before. So what does the miniHIL look like? That's a miniHIL board. I have the same setup on my desktop here. That's a miniHIL board. I show this a little bit later. And what we do is essentially with our miniHIL board, so that's the miniHIL board, we plug in a microcontroller, the real microcontroller that's running in your system. Doesn't really matter which microcontroller is. In this case, it's an STM32 for a pump control, Cortex-M4 processor, and we connect the pins of the microcontroller. Those are also on this those two pin rows here. We connect them with the other side, and that's also a microcontroller. It's a Cortex-M7, a very fast or the fastest, the biggest Cortex-M processor of ST. And and we connect all the IOs we need to test for the test run of the microcontroller with the test system. The typical IO interfaces are digital, analog, SPI, I2C, CAN, LIN, PWM. I guess you know exactly what I'm talking about. So all those low-level interfaces here. And in the end, we need to simulate the environment for this processor. So all the motors, all the batteries, all the sensors, and so on are simulated. We do not need very complex simulations for that. because it's important to get the system under test into the state where you actually can run it and test it. That's why we need the environment simulations. And then you can run test cases, automated test cases on the simulated system. But your system, so system under test, is the real system. So it's a real chip and the real software you're testing here. What does the development process look like? We develop first the simulation and the test models. So it's all model-driven development. You can easily integrate also models you already have. For example, a Simulink model can generate the code, integrate this into the simulation model or the test model here. Then we generate the code. It's C code we generate. We compile this, we flash it to the miniHIL board. In order to have hard real-time execution. So we can go down into the range of, let's say, 10 microseconds with a test case. Typical motor control simulation runs with 15, 20, 30 kilohertz. So it's really important to have a hard real-time system as a test system here for this kind of test. And in the end, we log the test cases and transform the logs into graphical views, into diagrams to really understand what happened here. On high level, things like a feature coverage report or requirement coverage report. Also on low level, which IO led to which error and things like that to really analyze exactly what happened here. And then you learn and iterate. Either you change your system under test and rerun the tests, or you change your test system, introduce new tests, and you run it. So it's all automated usually. Something special about our test case generation is we also can do combinatorial tests, state transition tests. So that's a method, standard method, where you can describe as a test case model the combinations or paths through your system. And for every path from initial to end, a test case is generated. And yeah, depending on the metrics you define, you get more or less test cases. So basically what we do is we generate for every path from initial to end to have a complete coverage here, we generate one test case. So every path here through the system is one test case. And it's automated. It also generates not only a diagram, but also a C code. C code again is compiled and is run automatically as test cases. That's really nice to have a good test coverage with less effort, much less effort actually. So it's a formal description of the black box behavior of your system, and then with in combination with a test case generator. So that's what a hardware in the loop test stand on your desktop looks like. So you have the miniHIL board, you connect it to your laptop or to your desktop with the development environment, and then you create the models and generate the code and run the system and test it. So that's a typical setup for one project or one person on your desktop. Also for the developer of the test cases. And if you have bigger projects, more people working on a project or longer running project, usually we go to continuous integration. You can hook this miniHIL directly up to basically any continuous integration server. So any code change of any developer leads to an automated checkout. So every change is tested on the continuous integration server within minutes. So you get a really fast feedback for every change, and on the content, and then you deliver potentially your software. And on the continuous integration server, we run the miniHIL software, and also we hook the miniHIL boards up to the continuous integration server. In this case, you see a rack. It's our own test rack for our own miniHIL tests, but that's basically also what customer projects look like. So for example, in this case, we could run 8 projects in parallel because you only need one miniHIL board per project. That's a simple, small, and inexpensive setup from the hardware side. We have customers that have racks with 20, 30 projects in one rack. So every change is checked out, built, tested, and potentially delivered if you want to. And even if it's only delivered to the system tester that really takes the drilling machine and drills hole into the wall, or flashes it into the ECU and gets into the car and drives around. But he will most likely not find any, or at least only a few software errors, because that's what the miniHIL is all about, to find those integration and software errors very early in the process. So every code chain of every developer is really tested within minutes, and you get an email, for example, if the test fails, the system knows who did the last commit, and you get an email and nobody else. And you can fix it after 5 minutes. You still know what you did. After, let's say, 2 months, you're probably not even in the same project anymore. So where do we use the miniHIL? Basically in any domain where there are 16 or 32-bit microcontrollers. In some cases, we also have 8-bit microcontrollers, in some cases 64-bit, but the typical microcontroller is 16 or 32-bit, because those are the applications that are usually very, very focused on I/O, on heavy use of I/Os. So you see all the domains. We have basically projects in all those domains, and even some more probably. For example, Hitex as our partner, they have some very nice railway projects, also automotive projects a lot. We also have a lot of automotive medical projects, and so on. So let's make a little demo of the system. I prepared a demonstration setup. On the right side, we have the microcontroller. It's an STM32. Could also be an Oryx or TLE or XMC, whatever it is. In this case, it's an STM32. I again show you the camera. That's the Cortex M4 here. That's the right side here. And we run a motor control application. Could be in a seat of an airplane. It could be in a pump, in a lubrication pump, or an oil or water pump, or it also could be in a medical device, blood filtration, or whatever it is. You have a lot of microcontrollers that control a motors or drives. And we have, in this case, a BLDC motor control system. So we generate 3 PWMs. The test system is measuring them, running the plant simulation for the motor, and generates 3 Hall signals as digital outputs. And the control for speed and direction and so on is done via UART. This could also be CAN, LIN, or whatever it is. It's just a little demo application, but it's a highly relevant demo application, I guess. And to give you a look at the electrical behavior of this test case, I can show you a signal log of it's a Salea logic analyzer directly at the signals on the board. So, for example, those are the block commuted BLDC PWMs. You control the BLDC motor with. They go from right to the left. Then we generate the Hall signals, the sensors, as digital outputs. They behave exactly as a real motor would behave. And here, that's the control over UART. So in this case, we change the duty cycle or the speed of the motor. In this case, the duty cycle goes from 50 to 90%. You can see this directly on electrical level. So sometimes it's really good to see on electrical level what your test case does, especially if the test case fails. You want to know why it failed. And hopefully it's not the test case that failed, but the system under test, because then you've detected a bug. So let's have a look at the real software here. Again, that's the setup on my desktop. connections here with USB to the PC. That's the power connection, and the debugger. If you want to debug directly, you can also do that. So let's open the IDE. That's an Eclipse IDE. We plugged in our all the miniHIL plugins as Eclipse plugins, and let's start at the motor, at the model for the test model level here. So everything that's in this box here is software that runs on this microcontroller, so on the test system. The system under test is your system. So however you develop this, usually we do a black box test, so we don't care about the way you develop, but it's important to develop the test system here. So everything inside this box is the test system. Down here we have the adapters for digital, analog I/O, UART. We have the Hall generator to generate the Hall signals, and we have the duty capture unit here with 3 timers to capture the PWMs. And here up here we have the motor simulator. So we capture the 3 PWMs, feed them over this interface into the motor simulation. The motor simulation generates or calculates the new speed and feeds the new speed over the Hall generation interface here into the Hall generator, and the Hall generator generates those 3 digital outputs. So now we need a behavior. That's the structure of the system. We completely generate the code out of that. But we still need a behavior, because the simulation is not only structure, it also needs a behavior. And the behavior in this case is a state machine. It can be manual C code, it can be a state machine modeled here with eTRICE with this tool. It also could be a generated C code from a Simulink model. Depends on if you already have a plant model, you don't need to develop this model in our software here. You can also use your Simulink plant model. In this case, that's a very simple motor simulation, plant simulation. Here in the state machine, if you get from the PWM input the new duty cycle measurements, we memorize the actual duty, and then we calculate the new speed, and we generate, we send the information about the new speed to the Hall generator. So Hall gen out, so I can use all the interfaces directly in my model. I could also, for example, now change the direction of the simulated Hall generator, for example, to inject an error, and then we could see whether the system under test reacts correctly by shutting down all the PWMs and throwing an error message or whatever it is you expect as an answer. Yeah, so that's the way you can model behavior of environment, or also do monitoring or whatever it is you need to do in your test system. So that's basically the I/O and the simulation part. And now we also need an automated test case. Now the system is up and running with the motor simulation. You can already run your system in this case and do something with it. You bring it to the right state. And then we connect the motor simulation and the UART with those 2 ports with the test case. So and here we also need a behavior. In this case, the behavior is not a state machine, but it's a test script. A test script that can again directly access the simulation elements or the IOs to stimulate the test cases, or the system under test, or to monitor it directly or indirectly via the simulation elements. So here you see a step, very simple step for a test case. So a step always consists of an action and a reaction, or several actions, several reactions, or only an action, only a reaction, depending on what you want to achieve. And if you change the model here, the textual model, you see always the graphical model here. That's only a viewer. It's updated automatically, so you always have a consistent documentation. You can also generate this as a document then in the end. And for one step, that's not so interesting, but if you, for example, we aggregate steps into sequences, you have a sequence with all the steps. That's already a bit more complicated. And in the end, on top level, you have a test suite. And in the test suite, you see all the test cases, all the steps and all the sequences directly in the test case. That's very important to really have the context, because here you do not know what really happens. That's good to develop, to aggregate, to abstract, but in the end, you need to know when a test case fails, what really happened here. And that's the documentation of what you expect. And then you run the test case, and then we have the same diagram again for the logs then. One special thing I would like to show you is the state transition testing. So based on the steps and sequences, you can create a state transition test. So for example, the same test is run with duty of 10, 50, and 90%. And now if I want to add more combinatorial information, the same test case is run again with the other combinations. Or for example, I could say change direction. I want to go do something else. For example, I want to go to brake, and while doing this, activate motor control, whatever. So you've seen this one here was new, or activate brake, yeah. And now we generate, I don't know, 10 test cases more to really cover all the combinations possible to run the test cases. So let's take this out again. So that's how you describe the test case. Now let's run the system. I show you the system under test, and I show you a graphical user interface. That's a graphical user interface you can run separately. If you, for example, are a developer and would do not develop the test cases, but just want to run the test cases as a regression test to make sure that your system still works after your change, you just connect this GUI to the test system. You see, if I change something, you see the LED, the red one, it's connected. But forget this one. The most important part is the automated part here. If I run a test case here, for example, let's pull a UART cable here while I'm running the test case, so I can show you that it's really live. So I'm pulling the plug here. Now it fails. Now I put it in again. Now the test passes again. And in the end, I get an information, for example, here, the test motor control speed failed. That's interesting, but now I really want to know what happened. So let's go back to my logs. And here for the graphical user interface, we have the traces. So the integration test failed. You can open this in Eclipse. You can also open this just in a regular browser. That's the Google Chrome, for example. That's just a scalable vector graph. Yeah, we look for the first test that failed. I click on the place where it failed. There, the timeout came. And again, the development environment opens and shows me exactly the place in my test model where it actually failed. So set duty failed, set duty, that's exactly the right place where it failed. Okay, so last thing I want to show you is we talked before about complete automation. That means whenever you commit something, I want the test cases to be executed. In order to this, we have to disconnect this one here. And I've set up a continuous integration project. In this case, on a Jenkins server, could be any continuous integration server. And what I'm doing now is I'm going to introduce a little error. Let's look for duty cycle. Yeah, here we have the set duty. I'm going to make a little sabotage here. Let's take this out and change the duty cycle statically to 20%. So this should lead to an error. And here you see the change I made. It's a Git repository I have here locally on my laptop, but of course usually it runs on a continuous integration server. I add the change and now I commit the bug. Of course, I know I did a bug, so I commit it. And what happens now? The repository is supervised or monitored by the continuous integration server. And the continuous integration server, when it detects the change, automatically starts to build the project. So it checks out system under test or test system, builds the project, and runs the test cases and creates the reports. So let's see what happened here. Takes up to a minute. Let's have a look at this. Yep, now it starts. Yeah, I committed the change. Yeah, here now you see it detected the change and now it starts to run the project. So let's have a look at the pipeline. That's the job that just started. It already checked out the code. It assembles the project. Yeah. All command line. That's why it works on any continuous integration server. And after, I can show you this here. And now it's flashed. Here you see the LED stopped. So it's really flashed. And the system under test is flashed as well. And now the tests are running automatically. And that's just a logging for people like you and me. That's actually the old logging we have. We let it in so that you really see when it's running that something happens. And here see we have only 21 test cases passed and not all the 23. The project is red now. That means, and usually you get an email because you're the last one that checked something in. And now the project is yellow. So I have a look at what happened here. And I see, okay, those two test cases failed. It's the demo integration test. Again, I can click the demo integration test. That's now the test on the server. So I don't even have to run the test myself. And I just click and it opens my IDE. If the IDE is open, it opens the right place where the test case failed. And we also generate a couple of other reports, like here the feature report. So those are the test cases that failed. And the requirement 10, for example, is not covered now because this test case failed. And we also generate the complete documentation about the test cases that should have run, and also about the reporting about the actual execution of the test cases. Okay, so that's a very fast introduction of the miniHIL, what we can do here. And yeah, thanks for your attention. If you have any questions, please write them in the chat. We will answer them after the webinar, or please contact Michael Weiss from Hitex or myself if you have any further questions, or if you want to discuss any problems or use cases. Don't hesitate, or if you have need for more information, please let us know. Okay, so that's it from my side. Thank you.